All right, good morning everybody. Welcome to today's webinar. My name is Martin Atkins here at the University of Waikato, and I'll be taking the webinar today. And the webinar today is on off-design operation of pump systems. So we're going to continue on talking about pump systems and their importance, especially from an energy point of view. And just a reminder for those that may be joining us for the first time, and a reminder for those who have joined us before, this webinar is going to be recorded and it will be available to view later on via the ECA Business website, and also there is a YouTube channel that ECA is running that has previous webinars from last year, and these webinars this year as well will be up there available to view. Please feel free, if you have any questions, to type them out and send them through. We may answer them as we go along, or we may just leave them to the end and deal with them then. But feel free also to fire any feedback through and any other topics or things you would like us to cover in these webinars. We have a pretty comprehensive list of topics coming up through the year, but there's always room to be able to focus on things that people think are useful and feel they need to be covered. So without further ado, we'll carry on. Okay, so just a brief outline of what we're going to cover today is we're going to briefly go over why we're looking at pump systems. Then we're going to talk about what does off-design operation mean. We're going to cover what the consequences of off-design operation are in pump systems, and also talk about non-ideal flow conditions and the impact that they have on our pumps and our pump systems, and some of the negative effects that we get from them. And then we're going to talk about some of the remedies that can be employed in order to do that. Okay, Jonathan. So this webinar mainly is more to do with pumps than fans. A lot of these issues do not have as much effect on fan systems, although James Neal will be, I think the next webinar in a couple of weeks is on fan systems. And so a lot of the non-ideal flow conditions, such as cavitation and things that we'll talk about, have less application to fans, obviously, but the next webinar will be on fans. So certainly if you have any specific things that you want covered or looked at in more depth, then feel free to get hold of us, and I'll make sure James is away today, but I'll make sure that he covers them. So thanks for that, Jonathan. And then finally, at the end, we'll talk about where to from here. Yeah, that's right. It's really around compressible fluids is what we're with fans, whereas in pump systems we're talking about non-compressible fluids here. So there is a bit of difference, and certainly we'll talk about that as we go through. Okay, so why are we looking at pump systems? And this is a little bit of a reminder, and we've talked about this in depth before in previous webinars. Pump systems are a high percentage of industrial energy use, especially electricity, and around 75% of pumps are estimated to be oversized. And so that has some large implications on both energy and maintenance and reliability of pump systems, and many of the problems that we encounter have to do with pumps being oversized. And certainly today, as we talk about non-ideal flow, that is the biggest factor is oversizing of pumps. And there's large potential savings by sorting out these problems, and these problems are quite common and widespread, and so they are fairly easy to solve if you're willing to put in a bit of time and effort. And also it's important to view pumps not just as the pump on its own in isolation, but also to recognize that the pump is part of a whole system, including piping and control and those other things. And so taking a systems approach is really important and not just focusing on the pump. Today we actually are going to focus a little bit more on the pump itself, but remember that oversizing of pumps has to do with not really understanding the system well. And so we'll talk about that as we go through. Now I keep putting this slide up around the study really to show that this is a big problem in industry, and many of our pump systems are affected by low pump efficiency and also a lot of downtime to do with maintenance. Things like seal leakage and things like that are really all symptoms of oversized pumps and having this off-design operation of our pump systems. And so that's what we're going to focus on today and really look at, well, where should we ideally operate our pumps, both from an efficiency point of view and a reliability point of view, because those things are very highly correlated together. Okay, so let's talk about what do we mean when we talk about off-design conditions. And what I'm going to do briefly is just review our pump curve here. So I'm sorry if this is going back to basics for some of you. All of our pumps that we have, there will be a pump curve, and it may be buried away in the archives, but this becomes a very useful, important piece of information to have. So if we just look at a pump curve in more detail here, okay, we have basically what the pump curve does is it expresses where the pump will operate as a function of flow rate versus the head or the pressure that will be delivered by the pump. And we have, in this particular case, we have different impeller sizes. That's the performance curve for each impeller size. And then we have lines, these lines here. If I just bring up my highlighter, these lines here are lines of constant efficiency. Okay, so if we're on that line, okay, this line here, which is not always to be found, is the minimum flow rate that we need to have for our pump. Okay, if we operate below that line, then there can be some very negative effects. We're going to talk about that in a little bit more detail, but do recognize that there is a minimum flow that you need to operate your pump at. If you don't, then there will be some big problems. And so what the pump curve does is it basically tells us about the performance of the pump and also its efficiency. If I go back one slide, typically there's also other information around what the required net positive suction head is for the pump as a function of flow rate, and often there'll also be what the power requirement is as a function of flow rate is as well. And so there's a lot of information to be found on these pump curves. And obviously we're operating at a point on that curve. Okay, so for example, this is the best efficiency point on this curve, and it happens to coincide at 475 cubic meters per hour. The head that the pump will deliver is 53 meters, and the efficiency is around 79%. Okay, that's the pump efficiency. Obviously, as we move away from that point, our efficiency drops, our flow rate will change, and our head requirement will change. And so we only operate on that particular curve. Now, the trick is to know, well, where are we actually operating? And so the first thing to recognize is that we're always going to operate at the intersection of our system curve and our pump curve. That is the operating point. And so depending on what our system looks like, whether we have our valves open or closed or whatever that may be, that will then change the system curve and we will change our operating point. And we only move up and down the pump curve as we
Muted. Unmuted.
Sorry, I got muted for some reason. Can you still hear me okay? If you can't, please send me through a message. Okay, thanks. Okay, so we will only ever operate along the pump curve where the system curve will intersect the pump curve. Okay, so what we need to do now is just define some different operating modes. So we talk about continuous operation of a pump, and that is where you can run the pump continuously and expect many thousands of hours of operation without any real damage or excessive wear of the pump or its components. And pumps are designed to operate, thousands of hours without really any problems, and so that is continuous operation. And we'll come back and talk about that in a moment. Then we have what we call short-term or intermittent operation, and that's really, we have upset conditions, upset process conditions, or abnormal operating conditions. So we're really operating away from our design point, and what that does, and we'll see why that is a bit later on, that actually introduces premature wear into the pump because the flow within the pump and to the pump are not ideal. It hasn't been designed for those conditions, and as the name suggests, this is short-term or intermittent, and so we wouldn't expect long-term operation under these conditions. And so people define what they mean by short-term operation differently, but typically you'd expect it to be around less than 100 hours per year. It may be more, it may be less, it really depends, but I guess the concept here is we have continuous operation where we operate most of the time, and then we have these sort of start up and shut down and upset conditions, and we really want to avoid operating there longer term. The other third operation condition is minimum flow. As we said before, all pumps have a minimum flow that they need to see, and what that flow rate is really determined by three main criteria. One is the temperature rise that we will get in the fluid, okay, and we'll talk about that a bit later. The second is hydraulic consideration. So this is things like vibration and excitation forces. And as we go through, we'll talk about non-ideal flow conditions, so the flow that is occurring in the pump when we have these reduced flow, especially below this minimum flow rate of our pump, and that can put huge stresses and vibration onto the pump because of the flow that's going on. And then the third one is once we reduce down close to or below our minimum flow rate, then the amount of cavitation can increase quite drastically, and the intensity of it also. And so we can do some major damage to our pump, both the impeller and the housing, as we go below this minimum flow rate. And so often that minimum flow rate is actually specified in the pump curve, but if it's not, there are some rules of thumb that you can then use to avoid that. We'll talk about that. So here we have our typical pump curve, and you'll notice that here is our best efficiency point here, okay, BEP, and ideally we want to operate our pump within a very narrow range around that best efficiency point. Okay, and typically that's between about 80 to 110% of the flow rate at best efficiency point. That's where we want to operate continuously within that range. So when we do our design of our pump system, we need to select a pump, and so where our flow rate and our head requirement, we have our pump operating at that best efficiency point or very close within that range there. Now the allowable operating range is actually much wider. So the pump will operate obviously anywhere along that pump curve. If we have our minimum flow here, this is sort of our minimum flow rate that we need to have, then this whole range here is sort of the allowable operating range. And so what we mean by off-design operation is really anything outside of that preferred operating range. It may be to the right of the best efficiency point, or it may be to the left of the best efficiency point. Okay, so as we go through the webinar and we talk about off-design operation, we're really meaning anything outside of that preferred operating range, which is actually quite narrow and fairly close to the best efficiency point. We're going to talk about why that is and some of the things that go on in our pumps as we have this off-design operation and some of the consequences of those. Okay, so as I just said, for continuous operation, so this is, most of our operation of our pump system ideally should be in that fairly narrow range on our curve there. For short-term operation, so this is actually a very small percentage of the total operating time, things like startup, shuts down, process upsets, things like that. We can operate in these regions here without too many, negative effects, as long as it's short-term or intermittent. Okay, so that's really short-term, and obviously we want to avoid being in this region here below our minimum flow. If we're operating in that, then that's bad news, and we actually need to design systems and control measures in order to avoid that. So for example, often a bypass will be installed in order to make sure that the minimum flow rate is obtained even when process demand is lower. Now, we talked before about oversizing and how that's a major problem. Basically, when we oversize a pump, we end up operating somewhere in this region here. And so that becomes a problem, and we'll talk about the effects of oversizing and these non-ideal flow conditions that we'll talk about. So before we move on, if we just talk about why so many pumps are oversized and we actually end up operating continuously outside of our preferred operating range. First of all, often designs are future-proofed, and so we're going to expand our production facilities, or demand will expand in the future, and so we size a pump that is bigger in order to anticipate any future production increase. Now that may or may not happen, but a very quick sort of life cycle or total life cost of ownership, or whatever you want to call it, that can quickly show what the actual economic cost is in oversizing a pump for the future. And often what you find is there's ways that you can still achieve good operation of your pump and also future-proof your design. So for example, you may specify a larger pump housing and have a smaller pump impeller that then can be increased later on. and you can quickly do the cost-benefit analysis of that if that is a real issue. But often that's put up as a bit of a smoke screen. The second one is safety factors or anxiety factors, and this is where really we're not too sure what our demand is going to be, and often that has to do with the head requirement. Our flow requirements are fairly well defined usually, and so if we're not careful, safety factors can be added in, and so especially if different people along the chain, like the design engineer, the consultant, and the supplier, put in these safety factors or uncertainty factors, then we can very quickly have an oversized pump, and it doesn't take too much additional safety factor in order to get quite far away from this best efficiency point. We've got poor system and poor piping design. Urgency, often, things may go tits up, and so we're interested in just getting a solution quickly. Often we're replacing like for like, so we're just replacing one pump for the same one. Risk adverse and things like that. Now, thank you, Paul. Yes, some of these things can be offset with VSD controls, and we've talked about that in previous webinars around, when do I need a variable speed drive? And certainly they are a good option in many cases. However, there are some things to be aware when using VSDs, and so they're not simply sort of the cure-all, and there's no real substitute for good system design. Certainly, if you put a VSD on an oversized pump, especially for a new build, then there's a lot of extra capital that is tied up that doesn't need to be with a correctly sized pump. So that is something that we're going to talk about a little bit more later in the year. Is we'll talk about what the advantages and disadvantages of variable speed drives are, and when they're the ideal and when perhaps there are other more efficient and cheaper options than that. But that's a good point, Paul, and we'll get to that a bit later. Now, previously, when we've talked about identifying pump systems that are potential candidates for energy reduction, we've talked about some indicators for inefficient systems, things like throttled pumps, pump systems with bypass or recirculation, multi-pump systems, etc., etc. And the ones that I've highlighted in bold here, throttled pumps, cavitating pumps or valves, high vibration, noisy pumps, things like that, pump systems with high maintenance requirements, and systems where flow or the head from the pump have degraded over time. These ones that I've highlighted, these are actually indicators where you're operating at these off-design conditions long term. This is not just you're having some short-term operation, you're actually operating away from that preferred operating range, longer than you should be. And so when you operate your pump at these off-design conditions, there are a number of what we call non-ideal flow conditions that occur within your pump. Okay, and we're going to talk about those, but if you think about pump design, what the pump designer is actually trying to do is design a pump that is, robust, reliable, but that will operate at a certain point in the most efficient manner. And so what they try and do is you're trying to minimize the losses in your design. And there are a number of different losses that make up why we have a pump efficiency. Okay, so mechanical losses, leakage losses, recirculation, and hydraulic losses. So we'll just briefly go through each one of these. So mechanical losses are things like, mechanical friction in your bearings, your seals, all of the mechanical components. There are frictional losses to do with that. The second type of loss is leakage losses. So you actually need some clearance between your impeller and the pump housing or the pump casing. And so there is a small amount of fluid that leaks between the impeller and the casing. Okay, but obviously in the design of the pump at a certain flow rate, you're trying to minimize those leakage losses in order to improve pump efficiency. The third type of loss has to do with recirculation. Okay, so you actually can get recirculation of fluid within both the suction or the inlet of the pump impeller and also the discharge because of velocity differences between the impeller and the vanes and things like that. And so that is another form of loss, and the designer is trying to minimize those, and that is how we get this best efficiency point. And then finally is we have hydraulic losses. So this is all of the friction between the fluid and all of the components of the pump. Okay, so that's sort of analogous to pipe friction, so friction in a pipe. We have all of these frictional hydraulic losses due to pump fluid interaction. And so when the pump is designed, those factors are trying to be minimized in order to increase or have the maximum pump efficiency. But as we move away, obviously the pump is fixed, and so as we move away from that best efficiency point, these losses are going to increase. And especially things like recirculation and leakage losses tend to increase as we move away from this best efficiency point. Okay, so there are sort of 6 things that arise from these off design conditions. Okay, non-ideal flow. So we'll talk about each one briefly. Okay, one, we operate at less than our best efficiency, and there are some energy consequences because of that. We'll talk about radial thrust. We change the forces that actually act upon the pump and the impeller itself. We'll talk about temperature rise in the fluid, especially at this below this minimum flow. The fourth one, which is really a big one, is around internal recirculation within the pump. So internal fluid recirculation, we'll talk about that. With high specific speed pumps, so these are your axial pumps, then your motor can become overloaded pretty quick, and we'll talk about why that is. And then finally, if entrained air or gas is an issue, then this can operating at non-ideal flow conditions can aggravate that and more, and we'll talk about what the effects of air in your pump is. Okay, so first of all, as we operate at these off-design conditions, then we move away from our best efficiency point. And so we're going to use more power or additional energy than needed in order to pump our fluid. And so there is an energy penalty which ultimately leads to an additional cost. Okay, so this is suboptimal operation, and there is a financial cost of operating away from here, not just in energy, but also in our maintenance. As we'll see, all of these non-ideal flow conditions actually reduce the reliability of the pump, and it can be quite a severe reduction in reliability. And so typically you have an additional maintenance cost that needn't be there if you were operating within that preferred operating range. The other effect on expenditure has to do with capital. If you're oversizing pumps, especially if you do that significantly, then bigger pumps tend to cost more money, and so there's additional capital cost or capital expenditure that you didn't really need to have, especially then if you have to go and put a large VSD on your pump in order to reduce it. There's additional costs that may not have been incurred if the design was done correctly to begin with. Okay, so there's a real financial penalty as we operate at these off-design conditions and outside of that preferred operating range. Okay, the second thing, as we move out of that preferred operating range, then our radial thrust that occurs on our impeller, that can significantly increase. So when we have our best efficiency, if we're operating at our best efficiency point, then we have uniform radial thrust on our impeller. But as we reduce our flow rate, okay, that's our Q, then what happens is the pump and the hydrodynamics of the pump was designed in order to, to get uniform radial thrust at the best efficiency point, but now we have non-uniform forces. And so what that means is our radial thrust on our impeller is now non-uniform, and so we will have a force that acts upon that, and that then puts additional forces on our shaft and our bearings and things like that. So what that does is that tends to, especially in bearings, that leads to accelerated bearing failure. And especially if we have high head pumps with large impellers, that radial thrust that occurs on our impeller can be quite large. And so this is one of the sources for reduced reliability of our pumps at these off-design conditions, is we have much higher radial thrust on our bearings, on our shaft. So if we just look at some numbers, okay, get my little highlighter. So here is at 100%, that's our best efficiency, that's our flow rate at our best efficiency point. Okay, so if we just have our full speed pump, okay, with a single volute, then our average radial thrust as a percentage of the maximum is fairly modest. Okay, so we're sort of down at this point, sort of 10% of our maximum. But as we move away from that, you can see that this curve here increases quite dramatically as we move away. So for example, if we're at 60% of our best efficiency flow, then we're roughly at about 60% of our maximum radial thrust. So that's a six-fold increase in the thrust that our impeller is seeing. Okay, Paul, sorry, I've just got a message that the slide is not changing. Do you see a graph of average radial thrust versus flow rate? Is that the slide that you're currently seeing? Okay, some people do, some people don't. Okay. Let me just clear this drawing. I'll just go back one and okay, hold on. I'm just having a Internet Explorer problem. Okay, can everyone see a slide at the moment? Okay, good. I'm running Chrome, but the computer came up with some internet. Okay, so this one should be temperature rise. Can you see that, Paul, up at New Zealand Steel? Okay, well, we'll carry on. Okay, so just to recap with the radial thrust, as we move away from our best efficiency point, that can be a significant issue because we now put a lot of increased forces on our bearings and on our shaft, and as we see, that we don't have to move too far from our best efficiency point in order to have quite a large increase in our radial thrust. Now, the third issue that we can run into, especially as we get close to our minimum flow rate, and especially if we have a deadhead our pump, then what happens is, if you think about it, the pump is still operating, you're putting a lot of energy into the impeller, which is turning the fluid, and if that fluid isn't able to move out of the pump, then that energy has to go somewhere. Okay, and so where that goes is to a temperature increase into the fluid and also the pump itself, the housing and the material. And so that can be a major issue, and you want to avoid that. In most instances, you want to avoid increasing the temperature of your fluid rapidly, especially if the fluid is volatile. And what you're really trying to do here is avoid flashing the fluid in the pump. When you flash a fluid, you have a huge volume change, and so that's never good for your system, having that large temperature rise and then flashing your fluid in your system. And just to give you an idea of the scale of the problem, it can be quite a major. The rate of temperature increase can be very quick. Okay, so this formula here, I've got the units in brackets there. It's important to use correct units. The temperature rise in degrees Celsius per minute can be estimated by this equation. Basically, the P shut, that is the power at shut off. Okay, so you can get that from the pump curve, and that is divided by the mass of the pump. Okay, so the actual pump itself, how much it weighs, the specific heat of the pump material, okay, if it's cast iron, and also the mass of the liquid in the pump, and also the specific heat of the liquid. Now, if we ignore the pump, the increased temperature in the pump itself, and we just focus on the liquid, that simplifies things quite a bit. Then basically we have the power that the pump will be drawing divided by the mass of fluid contained in the pump and the specific heat. Okay, so for example, if we had a 100 kilowatt pump and we had 50 kgs or 50 liters of water contained in that pump, okay, and we just ran the pump with no fluid moving through the pump, then the temperature increase is around 28 to 29 degrees C per minute. And so, if you think about that for a moment, if you had a problem with your control system or something and the pump did get deadheaded, a valve closed or something like that, then you could have a very rapid temperature increase of your fluid. And so if you don't have ways of mitigating that or controlling that, then that can be a big problem for you. And certainly, with the big emphasis on process safety, this is something to consider around, what if a system fails and a pump is deadheaded? Is it just going to keep running? This can be a potential hazard. And so, if we are operating close to this point, close to our minimum flow rate, then it really pays to have a really hard look at what are the consequences if this goes wrong, because the temperature rise can be significant. And especially if you have a volatile fluid, then bad things can happen. So this is one of the reasons we actually want to be out of that range, because this is a potential problem as well. Okay, the fourth. Okay, Paul, you should be on number 4 now, internal recirculation. As we move away from our best efficiency point, what happens is we get recirculation of the fluid both at the suction or the inlet and also the discharge of the impeller. Okay, and that can start fairly early on as we move away, and it can progressively get more severe as we move away from our best efficiency point. And so, okay, this is a little bit hard to see on this slide, but here we have the sort of the casing of the pump, and you can see the streamlines as we come through. Here's, if I get the highlighter out, here's the impeller. So this is obviously rotating, and we've got our fluid. And when we have suction recirculation, okay, this is this here, we get these eddies or vortices that happen at the suction, and they can be quite severe, and we can also have them occur at the discharge. Now you might think, well, why? Who cares? Why is that a problem? These can be very intense, and the velocities at the core can be very large. And you'll recall, if we talk about Bernoulli's equation, when we have a high velocity, we have low static pressure. Okay, so what happens is if we lower our static pressure due to high velocities in a vortice, then what happens is we can have severe and intense cavitation. Also, we can have pressure pulsations as well, and lots of noise. And if you go onto YouTube and you type in, pump suction recirculation, there's a very good video, I think from Ingersoll Rand, and they actually show, you can actually visualize this suction recirculation, and it can actually extend quite far back into the suction piping. Okay, so it actually can extend further than the pump, and you can get quite large pulsations, lots of noise, and lots of intense cavitation, which then can damage your impeller and things like that. And so often a lot of the cavitation that we find in pump systems isn't actually to do with a net positive suction head issue, but has to do a lot with recirculation and operating away from this preferred operating range. Now, as the impeller diameter is increased, what happens is the required net positive suction decreases. And so this all affects the flow in the impeller, and when that occurs is actually quite dependent on our impeller design. And so what this does is it affects our required net positive suction head, and we'll talk about net positive suction head and cavitation in another webinar in the future. But this can have a very negative effect, and we can have some damage due to this cavitation on our impeller. And where that damage occurs is actually a very good diagnostic tool as to what's going on in our pump and some of the problems that we're seeing. And so because you have this recirculation here, you get this stalled area of flow, and this is where the cavitation occurs. And so all of the damage from suction recirculation actually occurs on this side of the impeller. Okay, if it's cavitation from a net positive suction head issue, the cavitation actually occurs on the other side of the vane. Okay, and so I've got a better picture coming up of that. where if we have, let's what we call classic cavitation or a net positive suction head cavitation, the vapor bubbles actually form on the other side of the vein, and then they damage that side of the vein. If we have suction recirculation, it occurs on the other side. Okay, so that's a very good diagnostic tool, is when you're examining your impeller, especially if there's damage, is where is that damage occurring? Obviously, so here it is in a different way. As we move away and we have discharge recirculation, as we move further away from our best efficiency point, then that stall region moves further towards the discharge, and we actually get cavitation occurring at the discharge end of the vein. But it's on the same side as you would find your suction recirculation. So this is a very good way of determining what your problems are within your pump, is if there is cavitation damage, is where is it occurring on your impeller. Now, discharge recirculation, that has its own effects as well. It can cause instability in the axial rotation of the pump. Okay, especially for double suction pumps, this is a big issue. If you have a high specific feed pump, high specific speed, okay, so more of an axial type pump, then what can happen is you can have your motor overload at low flow rates, and we'll talk about that in a moment. So here's an example of damage, cavitation damage that occurs on the discharge end of the vein, and this is on the correct side of the vein where we know that this is due to discharge recirculation. Okay, so this damage that you're seeing in these two pictures has got nothing to do with net positive suction head. That'll be fine, but this is all to do with operating away in these off-design operating conditions and having large amounts of discharge recirculation, and you can see the damage which has been done there. Okay, so here we have our pump specific speed. So down the left end here we have sort of radial vein pumps, and then down this end we have axial flow. And here we have our head efficiency and power relationship. But what you'll notice for axial flow pumps, the power actually decreases as we increase the flow rate. Okay, and so as we move away from our best efficiency point, then if we're not careful, then we can have the power increase at low flow rates, and we can overload our motor as well. Okay, so that's something that can be an issue. And then finally, get rid of the scribble here. If we have entrained gases or air into our pump, then just on its own we have a performance decrease. And so here it doesn't take too much entrained gas or air to actually significantly reduce the performance of the pump, but the key thing here is to recognize that your minimum flow rate that you need to operate your pump is also affected. Okay, so the minimum flow rate is increased as we have higher and higher amounts of air in our pump. Okay, and if it's severe, we can airlock our pump and we can just have the impeller, it's not pumping. We lose our prime of our pump. So these 6 factors, as we've sort of already talked about, they can affect the reliability of our pump. So we can put a reliability curve on there as well, and as we get out of our preferred operating range, these factors that we've just talked about, they start to play more and more of a role, and then things like our bearing and seal life are negatively affected, which then obviously reduces our reliability. On the other side, as we move away to the right of our best efficiency point, then we can get cavitation. However, usually that's from a net positive suction head issue. And so, but the message here is that, if we're outside of our preferred operating range, we can have a very large decrease in the reliability of our pump. Okay, so pumps that have, significant reliability or maintenance challenges, then this is often a reason why is you're operating out of this preferred operating range for significant amounts of time. Okay, so what are some of the remedies? Well, for new systems, obviously avoid oversizing pumps to begin with. Okay, and we'll probably have a future webinar that talks about oversizing and how to avoid it, and how to deal with uncertainty in our design. But if we avoid oversizing to begin with, we can avoid many of these problems. And really, the key in order to do that is to understand both our flow and our head requirement. What is our flow profile? Is it just a continuous flow rate, or does it change over time? And the design of our system, especially the flow control system, is really dependent on what that flow profile is. So obviously, if you have a system with a very constant flow rate, then you don't really need a VSD. You can get away with just having a correctly sized pump. However, if the flow is highly variable, then having a variable speed drive or multiple pumps, that can be a way of dealing with and having an efficient system and also being able to meet the flow requirement. And so, understanding the flow and head requirements, how those change over time, and then selecting the appropriate flow control method is really how to avoid these off-design conditions for new systems. Okay, so that's very well and good, but for retrofit of existing systems, how do we solve an existing problem? Well, the first thing I would suggest is to actually conduct a pump audit. Pump system audit, look at the system, look at what the flow profile is, what is actually the demand of the system, whether it's an industrial system or whether it's a municipal water supply. How does our demand change over time, and what are the transient conditions that occur? Once you understand that, you can identify, well, how do we go from what we currently have, and what's the solution for that? And often just simply replacing the pump may not be an economic option. And so depending on the situation, things like a variable speed drive might be an appropriate solution, especially for a variable flow profile. If you have large changes in your demand, then a variable speed drive is often a very good solution. But remember, there are issues with that. If you have systems with high static head requirements, then implementing a variable speed drive, there are some cautions that need to be followed in order to do that correctly. The other option, and certainly for town water supply, things like that, is multiple pumps are used in the system in parallel, and so you can actually have very good control, sort of smart pumping, by using multiple pumps that come on and off as needed. Now, if you have a constant flow rate demand or fairly constant, then for a retrofit, there may be options for trimming the impeller. And so what that does is it reduces the head that the pump develops, and you can then shift, you allow a control valve to open, and you can then shift to a better place, and you can reduce some of these impacts from our non-ideal flow conditions. Or sometimes an impeller replacement may be an option instead of trimming. And in some cases, especially where it's the pump is indirectly driven, say with pulleys, then you could also look at changing the pump speed as well. That may be another way in order to move away, or at least reduce some of the effects of these non-ideal flow conditions. So for retrofits, I guess the main point here is if you do have pumps or pump systems that are problematic and that are operating away from this preferred operating range for long-term operation, then having a comprehensive pump audit and then looking at how do we solve these problems becomes a very important step in doing that. Okay, so some additional information. There is a New Zealand pumping systems audit standard with some quite useful information that was developed several years ago by ECA and EMANS, and so that is freely available there. There is the link, and if you get onto your Google machines, there's actually a very good three-part series about off-design conditions and some of the things that go on. And so if you Google that, then that's fairly easy to find. If you can't find it and you're interested in some bedtime reading, then please let me know. I can send you a link for that as well. Now we have some other webinars coming up. This is the first one for the year, and we will be running them for the remainder of the year, every second week or so. So the next one we have is on the 17th of February, fan curves and system curves, how they intersect. And so Dr. James Neal will be talking more about fan systems. So if there's anything in particular you would like him to cover, then please let us know. And then on the 2nd of March, we have Mr. David Addison from Thermal Chemistry Limited. He will be talking about and introducing industrial boiler water treatment and chemistry. Okay, and some of the implications from having good boiler water treatment and chemistry and some of the negative ones. And so David is a very good speaker. I've known him for many years, and that should be a very good webinar. And then we have others which will be sent out later on. Also, feel free to contact your ECA account manager. And as I said before, this webinar and our previous webinars are available to view at the ECA Business website there, and there's also a YouTube channel. So please, if you have any questions, feel free to send them through, and I will answer them. Okay, thank you for your question, David. We have one. It says, how much is there to gain in going to high efficiency motors? Certainly, that is a going to a high efficiency motor is not going to solve any of these problems. But if you go from say 85% to 90%, then you can very quickly determine what the energy saving would be, and you can determine what the what the cost benefit is of going to a higher efficiency motor. Certainly, I'm aware the new standards in the US around pumps and their high efficiency pumps. Some of those gains are actually by going to high efficiency motors. But simply changing the primary driver is not going to change it's not going to change where you are on your pump curve. And so yes, there'll be an energy saving, but if you are operating out of that preferred operating range, all of these other problems will still exist. But certainly if you're looking at a complete system and how do you solve this problem, and having a high efficiency system, then that is another option that you can look at. So hopefully that answers your question. Thank you, David, for that. Okay, I'll stay on the line for a couple of more minutes, but if there's Okay, thank you, Paul. So the question is around coatings on pump for efficiency improvement. Yeah, I'm aware. I haven't had too much experience with them myself, but I am aware of different coatings, and where that will affect efficiency is there's a couple of things. One is it may reduce the surface friction, okay, so you get an improvement in your hydraulic losses are reduced, and so the efficiency can be improved. Often they're used where wear is an issue. Certainly, if you're pumping slurries and things, then often they're more for a wear improvement. Wear is actually can be a big issue, especially for slurries and things where you actually wear the casing of the impeller and all the hydrodynamics are then changed as well. And so, your pump curve is actually distorted or modified as you wear both the housing and also the impeller of your pump. So, yeah, coatings are good. They're not going to solve all of those problems, but they probably have their use. But it really pays not to. There's a little bit of hype, I think, and so it pays to work through, what the actual benefits are, and do the cost benefit analysis of that. So that's a good comment. Thanks, Paul. All right. If there's no other questions, I will end the webinar. Thank you, guys, and we'll hopefully you can join us for our next webinar.